Today in class we talked more about work and how work relates to forces and relates to energy. And so to remind what we talked about work last time, work is defined to be some force that is acting on an object, that full magnitude of that force, times the displacement that it goes. I'm going to call that an R for right now, so that it's any kind of generic x, y, z, x prime, y prime, any of those, times the cosine of some angle between the displacement direction and the force, which, in order to not confuse from other angles we've been using for theta, we're going to use another commonly used variable for angles, that being lowercase psi, psi. So, this is the work done on an object by a force is equal to the force doing the work times the force that could be doing the work times the displacement the object moves times the cosine of the angle between the force being applied and the displacement. So, say that we have a person pushing a crate up an incline. And the incline is going to be at some angle theta, so that's raised some level above the surface. And the force the person is applying, we're going to call capital F, and that's in that direction. The force of friction, if friction were involved, would be going the other way. And gravity, of course, is going down. So if I were to draw a free body diagram for this, like we've been doing for other things, then we'd have our box. We'd have the force of the person, we'd have the force of friction going the other way, and we'd have the force of gravity going down. And so you could talk about the work done by the person, the work done by friction, the work done by gravity, and also the work done by the normal force. Because the normal force is on there as well, since it is the response to the crate actually being on the surface. And again, since the normal force is the normal force, meaning that it is the perpendicular to the surface, therefore it is coming out that way. And this angle here, between the force of gravity and that axis right here, is the same theta as that theta. That's our usual construct for the inclined plane. And so if we rewrite this as the x prime axis, as we've been doing, and the y prime axis here, we just tipped everything from x and y to x prime, y prime, and everything is completely consistent, we can look and see what happens when the person is pushing on the box, and what forces are involved, as we said, and what work therefore results. So, the work done on the box by the person is equal to the force of the person, maybe I should put that with a lowercase p. So the force of the person times the distance it's gone, the displacement it's gone. We're going to call that delta x prime, since, like I said, we're having our x prime and y prime axes labeled that way. So it's only going up delta x prime, and it is the cosine of the angle between the displacement and the direction of the force. So, for the person pushing the box up the incline, the direction between the displacement, which is going up, and the force the person pushing, which is also going up, is 0. So psi right there is 0, which means that the cosine of 0 is 1. And so the work done by done on the box by the person is just equal to the person's force times the displacement. Now, what about the work done on the box by friction? Well, in that case, now we have the friction force acting on the box, its magnitude, its full value, times the displacement, times now the angle that is between the friction, the frictional force, and the displacement, which the box is going up the incline. That's a displacement going up the incline. The friction force is going the other way because it's resisting the motion. So the angle between those 2 points is 180 degrees. So that's cosine of 180, which is -1. Instead of plus 1, we have minus 1, so that means that the work done on the box by friction is negative the value of that force times the displacement. So yes, you can have negative work. You can have positive work, and you can have negative work. And then we also have the work done by gravity on the box. Well, actually, let me write it the same way. So the notation is the same. We have the work on the box done by gravity. Okay. And so therefore we look at the force of gravity acting on the box times the delta x prime, since we're still talking about the same displacement as gone, times the cosine of the angle between the force of gravity and the direction of the displacement. So if this angle right here is theta, then this angle here is actually the angle between the force of gravity and the displacement. So that angle right there is going to actually be, in this case, is going to be 90 minus theta, but technically speaking, we're looking at this angle, because it is the angle between the actual displacement direction and gravity, so it is 90 plus theta. So we have cosine of 90 plus theta as I run out of room on the board. So the cosine of 90 plus theta, if theta is less than 90, would put it in the second quadrant. So if we look at this mnemonic I've mentioned in class before, where this shows which trig functions are positive in which quadrant, all trig functions are positive here. Sine functions are positive in this quadrant, tangent functions are positive in this quadrant, and cosine functions are positive in this quadrant. So all scholars take chemistry, that would be the way to remember this, or all scholars take calculus, depending on which one you like. If you don't like either, you can pick something else for that seat. But that means that if we're in the second quadrant, which is what 90 plus theta would be, then that angle is going to be negative. Now, we would want that to be the case because the gravity is going in the opposite direction of the displacement, because it is pushing it down the incline. So the work should be negative there. Now, the work done by the normal force is going to equal the normal force times displacement times the cosine of psi, being the cosine of the angle between them. The displacement's going this way, the normal force is pointed up, that angle is 90 degrees. So that's the cosine of 90, which is 0. So the work done by the normal force is actually 0. It's not contributing any work to the box. So the net work, then, the total amount of work that the box is experiencing, or because of all the forces that are involved, would be the work done by the person on the box, plus the work done by the friction on the box, plus the work done by gravity on the box. All that together would give you your net work. So that is the basic idea for how we would talk about work in terms of the force and the displacement. So it's the force in question acting on some object, the whole force you have, and the displacement times the cosine of the angle between the displacement and the force. Okay.